Thank you all for taking the time to attending the end of the day panel. This is Gene Roe, the founder of LiDAR News. We're very honored today to have an outstanding panel of LiDAR industry veterans and pioneers, and they're going to discuss some lessons learned from some of their more challenging projects over the years. So we have Marek Koltun from NavVis, John Russo from ARC and USIBD, Michael Raphael from Direct Dimensions, and Dennis Hirota from Sam Hirota. My job, as I see it, is to get out of the way. So I'm not going to take a lot of time to introduce people. I'm going to let you choose what you'd like to rather than reading some paragraph of experience. Welcome, John Russo.
Okay, I'll just quick introduction. My name's John Russo. I'm president of ARC and founder and president of the U.S. Institute of Building Documentation. My background, I'm an architect. I have degrees in business and architecture. I've been in the business of doing building documentation for a long time, 13 years in the practice of architecture, and then started my business 25 years ago doing building documentation. Today, going over some lessons learned and best practices. So I'm going to cover some things to consider before you accept a project. What to do when you face uncertainty, what to do when things go wrong, adding value. And I chose one project in particular that I want to go through with you guys today. It's our Fremont Street project in Las Vegas. And for those that either are or not familiar with the Fremont Street project, this is it's a project that spans 4 city blocks, basically. It's a large space frame structure that is about a quarter of a mile long. And on the underside of this, it has an LED light system. And this is kind of what it looks like underneath. Basically, this project was undergoing a renovation to replace all the LED lights on the bottom side. You can kind of see here the new LEDs being installed and the old ones being removed as those were being installed. Watchfire Signs was selected to do the retrofit, and Watchfire hired ARC to help them document the existing conditions. Was a little unclear at first what they wanted, and it seemed simple enough. They said, we need this structure scanned. And we said, okay, what do you need? And well, it became evident pretty quickly that it was going to be a challenging project. What they were really after were these subframes. They're 2x2 steel, and they were sandwiched in between these LED light raceways and the superstructure of that holds everything up. The other thing they were after were, in addition to the subframes, they wanted these clips and these bolts that are used to attach the subframes to the superstructure. And this was probably the most challenging piece of this, because these are not too visible from a laser scanning standpoint. So we told them we weren't sure if we could do this project. The other thing we were contending with was the structure had significant sags in the structure over the length of the space frame. And that meant that the Watchfire could not rely on the existing record drawings that were really well dimensioned, but because of all the out of plumb conditions, it wasn't going to work for prefabricating space frames. So what we ended up deciding is, you know what, we're not sure if we can do this, but we'll do a pilot project. And they authorized that, and we said, okay, we'll see what we can get. So we came up with a concept of trying to come from below and from above into these little openings on the underside to try and capture the clips and the bolts that were holding the panels up. Obviously, being nearly 100 feet in the air, we couldn't get a tripod right under this, and we were at too great a distance to shoot it from the ground. So we came up with a concept where we'd need to develop some sort of custom rig that we could get a scanner right up into these openings. And this is what we came up with. It took a number of iterations, but we ended up with this fully articulating rig that we could strap to this support column, and we could swing it around and position it into the opening wherever we needed. The first problem we encountered was the choice of our scanner here. We picked a BLK because of its lightweight, but that proved to be problematic. We spent a week on site in the first bay scanning these openings, and when we got back and registered our data, we discovered that we had a problem. The data was distorted, and really these columns were kind of peeling apart. And this is a single scan, so we knew we didn't have a registration issue. We just knew we had an issue. So we determined that there was a proximity issue. You couldn't get too close to the object with the scanner we were using. So we went back to the drawing board, had to redesign our rig and strengthen it to hold a heavier scanner. And this time we tested everything thoroughly in the shop before we went back out to the field to make sure that we wouldn't encounter the same issues. And everything looked good in the shop. So back out we went, spent another week collecting the same data with a different scanner. That proved to be successful on the bottom. We also had to go up to the top side and scan from above to capture all of the subframes. And this was probably the most physically demanding piece of the project. We had, there was no easy way up there. There were no catwalks. You basically had to be lifted up to the bottom edge of the barrel vaulted space frame and then climb up like a ladder and carry all your gear with you, all in the 90+ degree heat of the Las Vegas environment. At the end of the day, we ended up, we were successful capturing the subframe assemblies, and that worked out really well. However, we were not able to get adequate lines of sight for the clips and the bolts. And when we went back to the client and said it didn't look like we were going to be able to get that, they suggested that we do hand measures. So we said, okay, we'll attempt hand measures, and we set a very thorough double check process up because we know hand measures are fraught with errors. So we created these documents, and we were able to document the clips and the bolt holes using a hand measure method. However, it proved not to be a viable solution because it took way too long to document that way, and the schedule didn't have that kind of time. So we ended up having to propose some other methods of getting some alternate form of data that would be useful to the client. And at the end of the day, I'll kind of shortcut the lessons learned here. Basically, we learned, take time to learn your client's needs up front. This was a very complicated project, and only having 10 minutes to talk about it here, I can't get into all the details, but it was very difficult learning exactly what they needed. It took quite a bit of time. Know your limits. What are you capable of? What are you not capable of? In this case, this is nothing we'd ever attempted before. And So we weren't sure whether we could do this or not. Set the expectations early with your clients. Make sure they realize, if you're not certain and what the options might be, have thorough discussions up front. Propose a pilot project if you're not certain. In this case, the client said, okay, yeah, we'll accept a pilot project. We got paid for the pilot project. And then at the end of the day, the client could see what we could do, what we couldn't do, and we could make some decisions on whether or not to move forward. Don't hesitate to walk away. There was one point in this project where the client said that if they went to lift a new subframe into place and it didn't fit, we would own it. We would have to pay for it. And I said, I'm not good with that. There are too many factors that could go into that frame not fitting. And at that point, we said, we're not going to move forward. And they came back and they accepted the risk. So don't hesitate to walk away. Test new processes out thoroughly before you get to the field. It might save you some grief. And just plan carefully for risky environments. Again, we were climbing using climbing gear, and this was not a normal project. So just make sure you understand the risks on the project. And then know what your plan B is. If things aren't going your way, make sure you have a plan B in your pocket. Lastly, something else to consider is, how else can you help your client? And in this case, we identified an opportunity for the client to submit this project to an ENR contest, and they won an award with it. So they weren't aware of that, and that ended up benefiting them and us. So always look out for your client's needs. And that's hopefully I'm within my 10 minutes, Gene.
Yeah, very good, John. Thanks very much. So I think Marek is ready to go. Can you switch it over? Stop sharing, John, and let Marek take over.
So welcome, everyone. Very happy to be here, joined with the fellow panelists that definitely have much more experience than me, but I'm very happy to know them since I'm rather new to the game with my 5 years experience in laser scanning. And I have great experienced folks to look up to show me the ropes and how the laser scanning have been changing in the past 20 or 30 years since it was created. So not too much about me. I work for NavVis in the New York City office. The company is headquartered in Germany, and I just happen to like scanning. So I look for any excuse to just go out and scan some weird or crazy sites because I like the challenge. I like pushing our technology to the limit, and I like to see how big, how fast, how accurate I can get the data done. So what I wanted to show you today is share a couple of examples of the stuff that we scan and different projects. And where do we come from with our mobile mapping technology? Everything has started years ago and moved from total stations to static scanners to mobile scanners. Being with NavVis for 5 years, I witnessed our 3 generations of products. M3, which was big and bulky and not that accurate. M6, which was big, bulky, and more accurate. And finally, the VLX, which is much slower, much smaller, much faster, much more accurate. This is the first product that can compete head-to-head with static scanners that everyone else is using. And most of my clients, obviously, besides NavVis, also use a static scanner because the best approach is to use the right tool for the right job. So I have 4 little sites that I think will be interesting to share with the audience of what we have done and why they were challenging. The first one is San Jacinto Community College Glycol unit that I got to scan with Matthew Craig as a pilot project to see how VLX can perform in oil and gas or refinery environment. He had scanned it with his ZNS scanner. Took him about 8 hours, a lot of placements, got perfect data. It took me 8 hours to fly to Houston, scan the unit, to get a lunch with Matthew and fly back home, because the scan itself was just over 20 minutes. We did the data evaluation later, cloud to cloud, came out within about quarter-inch accurate, just as we were hoping it would come out. So playing a little video of how the point cloud looks like. And any type of environment like this is challenging for static scanners, maybe not because it's hard to get to, but it's challenging because the amount of detail, nooks and crannies, and all little objects, pipes, tanks, and everything else that has to be captured from multiple different angles. This means that there are hundreds of placements in a relatively small square footage-wise environments. With VLX, the scanning is completely different, because all you have to do is just walk around and do a lot of figure eights, looks, just to make sure that you can see that environment from different angles. So you don't need to take as many placements. I mean, there's no placement as a static scanner, but you just have to make sure that you go around every more important structure so you can capture it from every single angle. And instead of having a lot of blind spots and occlusions, we have much more complete point cloud that computes itself into one data set. So this particular site was about 20 minutes on site, and human processing time was literally just to start a project. So copy the data off from the scanner to the computer, select a folder to process, click a blue button that says start, and come back a few hours later to receive one unified body 7 file that I am playing the Novigon preview right now. You can see how the site looks. And here is a bit more detail how the site was captured. It was Matthew filming me going underneath the tower using the VLX as a semi-handheld device, taking it out to the places just to get better coverage, taking photos. Obviously, you have to pause for photos, but once you get some experience, you can, let's say, trick the system and stop enough to take a photo, making it seem like you're not really stopping. In that case, I will stop on the yellow block for a split second, take a photo, stopping in the middle of that staircase for another photo, and stopping on top of the staircase for another photo. Unreceived photos are used for virtual walkthrough aspect, now web viewer, and point cloud polarization. Another project that I wanted to share with you was a construction site at Boston College that we have scanned for a quick as-built verification. It was about 70,000 square feet, and it took just over an hour to scan. Our clients there have scanned the same site with static scanners, and took them a one long day because they had to wait for equipment and for people to move out from the site. So going on construction sites, even though the site might be empty, there's a lot of activity happening, and there's different floors. There's one sub-level there. Workers bringing materials, blocking the way, constant change. From week to week, the site changes. And if you are able to access certain sites last week, certain areas of the site, it doesn't mean you can go there this week. So every time you go to a construction site, it's slightly different building. And in order to be able to scan, process data, and do an as-built verification, you need to do it very quick. If it takes you a week to scan a large site, we're talking about sites that are hundreds of thousands of square feet, talking about scanning plus registering and delivering the point cloud, a week or 2 weeks later, the site doesn't look like this. So in construction sites, our clients prefer to go and get the data captured very fast because the project is moving with or without them. So if they don't check something in time, the project will just keep moving. And here's a little video. An example was we were doing a loop closure around the building. And in the beginning, there was an open passage. You could circle the building, but when I finished, they parked this forklift or something else, and I had to go under the trailer of a semi truck. Because if not, I would have to add another couple hundred steps to close the loop. And this little stunt saved me, I don't know, 5 or 10 minutes walking around just to finish the loop where I started. Third project comes from our clients from Skanska, from the New York City office. And a few years ago, they were working on a pedestrian bridge at the new LaGuardia Airport terminal. They wanted to do a quick as-built verification when one of those bridges, I believe it's this one on the left, was built. And I wanted to verify that after it got loaded, concrete got poured, obviously the bridge settled a bit. They just wanted to make sure if everything is within the tolerance because the bridge got loaded and heavy. So in that case, the structure was maybe 200 yards long. They wanted to do a quick capture. And it was an active site with a lot of workers. So what I remember, some of my colleagues came in with our scanner and scanned it over lunch break. What they did after is they took an EP7 file, which was registered in a state-linked coordinate system that the entire project for the entire airport was using. They had a bunch of control points on the ground. And even in the fly-through or the video here, you can see them as pink dots. And besides the scan itself, they also got the virtual where they could document how the building looks at the current stage of the process. And they can take measurements, see what's behind the walls, what's behind the ceiling, because when they scan it, there was no walls or no ceiling there. So looking right here, grabbing measurements, and it's very simple. You can literally see how tall, how much space do they have from the vent going all the way down. And I guess the video cuts here for some reason. The last project I have is for another one of my clients. It was the RFP bridge. It's a pretty big bridge. I think it's 5 lanes each way, so 10 lanes total that connects Queens to Manhattan. What they wanted to do there is, it wasn't a structural work, an old bridge. They wanted to do asset management, facility management use case, do a little bit of a model verification, just to make sure that all the features inside the bridge were modeled and nothing was missed. So what you see right now, this is the massive anchorage of the bridge on the on one side of the bridge. You can see all the structural steel, you see the balcony, and those massive pillars that are holding the entire bridge. And the idea here was the site was kind of hard to access. Static scanner would require a lot of placement to capture everything. And with the VLX, we just climbed up the staircase, walked around, and were able to capture the point. Then going on the upper level, getting all the way to the top deck of the bridge, and just skipping it a little bit. We have some videos, because this really shows like what acrobatic achievements you can do with our scanners, like moving around tight spaces, essentially anywhere where a person can fit, they can fit with a scanner, and it doesn't break slam. There are certain handheld devices which are great for smaller projects, but if you bring them into very tight environment, they might lose the slam itself. With the VLX, we were able to hold the slam, and having few control points, we're able to correct the point cloud afterwards. Another idea here, instead of going around turning, setting a VLX on a beam, making sure it doesn't fall, and then kind of crawling under. The device is on pause right now. It's not actively scanning, it's just positioning itself, coming through, picking it up, and scanning again. Taking it to the next level, climbing ladders. It's not something we do every day, but the device can be used without, you don't have to hold it. So you can just carry it on your shoulders. I'm gonna fall. Here you see I will have little trouble. I realized I was getting stuck in a pigeon net, but good thing it didn't pull me down. I just kind of pushed it back and went all the way up. The device was continuously scanning and positioning itself with the robust slam that it runs. And then finally, on the very top of the bridge, when you come through the VLX, if there's obstacles or anything in your way, you can push it away or just like open doors. It doesn't mess up the slam that much if there's enough features for the device to hold itself. That case could open the latch and just keep scanning. And this is as much as I wanted to show of some of the more difficult projects I was able to scan in the past 18 months.
Very good. Thank you, Marek. That's some pretty phenomenal footage that you had there. You and John both like the high thrill data collection projects. I can see that.
Yeah.
So we're going to turn it right over to Michael Raphael from Direct Dimensions, and looks like he's ready to go. Take it. Michael.
Okay, Michael Raphael with a company called Direct Dimensions. This will be my bio. I helped develop the device called the Pharaoh Arm many, many moons ago, and started my business in 1995 as a one-stop shop for 3D scanning. Over the past almost 27 years, actually tomorrow, we have done thousands of projects across a wide range of spectrum, from very large things, which we're going to focus on, to very small things and everything in between. So we work in a wide range of industries. We cross the boundaries of scanning and go across industries, across scales and sizes, across engineering deliverables, including complete CAD models of very intricate items known as reverse engineering. So we kind of cover the full gamut of 3D scanning and have a wide range of tools to provide these services. And again, we put people in the field that go across a wide range, including museums and industrial sites, and obviously facilities and sites. For example, aerospace is a big world for us. I came from the aerospace industry, so we are frequently scanning aircraft and items like that. We do ground vehicles quite extensively and have done many dozens and dozens of different ground vehicles and motorcycles and things like that. We have done, okay, here we go. Industrial components from widgets and things that if it's small enough, it gets shipped to us. If it's larger, we go to it. Consumer products, art and sculpture, all kinds of art. We do a lot of work in museums and with artists and fabricators of art, things like that. Okay, so let's dive into our world of 3D scanning. And you're seeing this one photo here showing a very early project that we were involved in. And you can see this is one of the earliest 3D scanning tools on the market, a Cyrax, what was it, 2400, I think. And this is just after 9/11 in 2001, where we were asked to show a demonstration to the government as to what 3D scanning is all about. Should something catastrophic happen, for example, in this case, for Abe Lincoln at the Lincoln Memorial. And we were able to go down and scan the Lincoln Memorial and much of the portico, and Abe himself sitting in the chair. And we walked back in several months later with a 3D print that you can see right there on the screen. So this was again in, well, 2002. We walked in with a print, and the folks said, well, this is great, but we want 2D drawings. So I paused just like that, and I said, all right, I'll come back in 10 years when you understand what we just delivered for you. Obviously, you cannot remake Abe sitting in the chair from 2D drawings, but the fact that we have a 3D print demonstrates that it is captured in 3D and can be remanufactured in 3D. Since then, we've done dozens of major artifacts and monuments, including the Tomb of the Unknown. We did a project. We do quite a bit of work in the, believe it or not, the movie industry in Hollywood. And just to show the scale of 3D scanning, this is a demonstration of us, or a picture of us scanning in Times Square in New York for the movie Spider-Man, one of the Spider-Men. We've done several. And ultimately, it was used for these types of scenes in the movie, that data. I'll add, by the way, that the Abe Lincoln was data that we did in 2001 was also used eventually for Night at the Museum, when Abe gets up and walks around in the middle of the movie. We also did a very interesting project in Washington, D.C. And again, a little bit of a lesson learned is to try and do this before the problem occurs or the calamity. Those that are on the East Coast might remember an earthquake that occurred south of D.C. And it did damage this building, which is the National Cathedral in Washington. There was extensive building damage to many buildings, and we ended up scanning several different projects because of that. But we did do this National Cathedral inside and out entirely, thoroughly, and created, in this case, 2D drawings, architectural drawings for the entire inside and outside of the structure. And you're seeing some of that here and some of these. And it was a very extensive project, and it was probably close to 15 years ago that we did this, or whenever that earthquake was. Right there, you're seeing on the right-hand side of the screen, actually, what's pieces from the pulpit. And this is the pulpit. I actually have it 3D printed that I'm holding in my hand. And there it is. There's a photo of the 3D print, just so you can get a sense of it. But I happen to have it in my hand for demonstration. This is another similar project, architectural detail in Annapolis, Maryland, which the State House in Annapolis, which is where the legislature conducts its business. A very decorative facility, as you would imagine, and historic. They were doing major renovations. We actually went to another building, captured architectural detail that they then reproduced and brought back to the State House in Annapolis. And again, I have an example of the architectural detail that you're seeing right there on that screen. So these are high-res 3D meshes that we're able to send to a 3D printer or any kind of a digital fabrication device for fabrication, for reproduction. And there is, again, a piece, that piece as well, and it created off of in this case, just a desktop printer. We did do more extensive architectural detail, and these are printed using nylon material, very kind of elaborate, kind of very sturdy, very strong material. And these were used literally to make patterns, to make casts, to make the plaster to put back in place on that project. Here's another one. This is a typical sort of around the light fixture. It's historic, and you can see the sense of it. We went up on a ladder and we used a handheld scanner, and we were able to scan and around and capture this completely. Ultimately, we produced a 3D print, and you're sort of seeing it here. And this is a very small model. The thing was probably about 3 foot in diameter. And I'll add that this was reproduced using 3D printing. We did this by making small pieces, putting them together, and making a 3 foot diameter piece that goes back up on the ceiling in another room. Another very interesting project, and this is really highlighting the high accuracy scanning and reproduction. As you can see, that's the Bergdorf Goodman building in New York City. It's just below Central Park. And it's a very decorative, ornate opening, a doorway, their front door. They wanted to reproduce all of that decorative material on the opposite side of the building and another fairly nondescript doorway. So they hired us to come up, and we 3D scanned all of that doorway area. And you can see some of that stone material on the right-hand side. And as I show you the scanning, you can see all of that captured at sub-millimeter resolution and accuracy, as you would expect it, as you would need. Now, we also did what we call digital sculpting to restore elements that had been broken or damaged or worn due to weather. And all of that was reproduced in the computer in 3D in a mesh format, ultimately for fabrication. You can see some of that right here at this point, some of those meshes. One of the things to point out, it was rather interesting, we happened to take a scan of the opposite side of the building for that door and realized the aspect ratios of these two doors were different. They did not know that. So the lesson learned here was we fortunately did that capture, and we were able to fix the data so that when they reproduced and manufactured all of these pieces, it would fit around the doorway on the other side, which again had different dimensions. And there you can see the very clean white marble that has been installed on the back side of the building, below on the opposite side from Central Park. Okay, this is an example of, again, our earthquake damage. This is a building at Georgetown University in DC, in Washington, DC. And you can see sort of on the lower right, a column structure that they wanted to understand whether it swayed, whether it moved during the earthquake. Unfortunately, of course, we didn't know what it was before the earthquake. We only know what it is relative to perfect plumb. And those colors indicate deviation from perfect plumb, vertical. So we were able to produce these types of accuracy plots and reports so they could at least understand where it is sitting today, not necessarily had it changed. Another very large structure, a civil application. This is actually a graving dock, what's called a graving dock, or otherwise known as a dry dock. This happens to house or manufacturing of submarines in Groton, Connecticut. And we scanned several of their graving docks up there and produced, as you can see in the middle, a very detailed 3D CAD model, ultimately delivered in what's known as SolidWorks, which is a manufacturing CAD program. And that was used to do quite a bit of extensive renovations in these structures. And then lastly, I think this is it. We scanned in Smithsonian, the Air and Space Museum. And I really wanted to point out that not only did we go there to simply scan the building, which was for architectural purposes, but while there, we were able to actually capture many of the, in this case, aircraft that were hanging from the ceiling and located around the floor. And it was fortuitous to the organization, our customer. They were able to actually use models that we created of the actual aircraft, the design of the exhibits, ultimately for HVAC and wind flow purposes within the design of the retrofits that they were doing in the building. So that was rather interesting. Oh, and I do have, this last one I think is a brewery conversion project. So we do every bit of the same type of architectural scanning that most folks do in this industry with our long range scanners. And this is a perfect example where it's captured. This is down in Memphis, Tennessee. You can see a nice cross section of this old building. And ultimately this was modeled by us into Revit and delivered for subsequent redesign by the architects. There you go. That's me, and that's just about 10 minutes. And they didn't think I was going to do it.
You proved us wrong, Michael. Absolutely. That was phenomenal. What an overview. Absolutely. And Dennis, you're one of the few people who I think could follow that and probably keep up with them. So it's over to you, buddy.
Okay, well, Sam Hirota Inc. was founded by my dad in 1963, so we're moving on to our 60th year. We've partnered with world-class companies such as Regal, Zoller and Froelich, NavVis, and Esri from the US. All right, I listed the 4 things that most people don't know about me. I spent 9 cold winters in Ann Arbor getting 3 degrees. And the other ones there are all a result of primarily that. The big unknown was yesterday was my 82nd birthday. Anyway, the next slide is what we're going to talk about, which is the Cascade project in the center of the Jonah Kohio Kalanianiole Federal Building here in Honolulu. We were fortunate to win the Grand Conceptor Award on March 10th, which was the award given by the American Consulting Engineer Companies of Hawaii. The next slide shows you the NavVis VLX point cloud, which we scanned in the courtyard, the center of the federal building there. And the project goals were to basically use as great a detail as possible to capture this approximately 30 by 20 foot concrete series of 35 fountain heads made of concrete that was disintegrating. So you can see the best practices there. We did some site visit testing. We used multiple sensors as a check and the software file types for interfacing so that we could use multiple sources and registration using grid targets. The next slide shows Landmark Services, who was a contractor to generate the Revit model at the end that the GSA wanted, who was the client. But talking to Larry and Sherry, we decided to try to attempt to, instead of using survey grade scanners, to go to a metrology grade, which they and we have, which is an Artec Leo. The next slide shows Laser Larry doing the scan with the Artec Leo. And it's a handheld scanner with a 0.2 millimeter resolution, combining photogrammetry with structured light, and it's great for capturing detailed complex shapes. It has a limited range, and so there are difficulties with registration of large objects such as this fountain. The next slide shows the NavVis that we have, and Marek described it in some detail, so I won't go over all the details, but it's a SLAM scanner. And We had the ability to do a fast scan. We scanned the courtyard in less than 20 minutes for about 70 million points. And I personally think it has the best color for scanning visualization, which was important for this project. It left no tripod shadow and generated a 5mm grid. And so we used it for the Arctic Leo scan that Landmark was putting together. The next slide shows the Zoller and Froelich 5016. We have a pair of 5010Xs as well. And we borrowed the 5016 from ZNF. And the great thing about it is that you could get it into close range situations without a tripod. And we did not use a tripod and generated no tripod shadow. And we used the ZNF 21 scan positions to register the 1,400 photos that we're going to see in the next slide. Okay, here is the epic reality capture model that was generated using the ZNF 5016 and the 1,400 Nikon 46 megapixel images that we took. So we combined it, loaded the information automatically into reality capture. So there was automatic input of the Nikon images as well as the ZNF scan position files. For each scan position, they generated 6 scan positions and then used the software to register and merge the entire model. You can see here as a detail, these ribs here are approximately 10 to 15 millimeters apart. And these pyramid features here are somewhere between 30 and 40 millimeters in size. So you can see the very detailed information that we obtained from this model. The next slide shows the epic Unreal Engine model that we generated by taking the LAS export from reality capture and loaded it in. And we are trying to, as not part of this project, but as an external test to see if we can run the 35 fountainheads with water using the Unreal Engine. The next slide shows us the post-processing equipment that we used, which I built approximately a year ago. And so we have a pair of these Threadrippers. One is a Threadripper Pro, which has 512 gigs of RAM. And so we're able to process these types of things, which are shown on the next slide. The software overview is shown on the next slide. I just want to make mention, the list is here, but basically, we use the GeoMagic Design X to mesh at high resolution the unstructured scans that we got from NavVis VLX. And to be able to use that in the Arctic Studio 16, which basically took several 100 million polygons that we got from the Arctic Leo and reduced them to approximately 10 million. We then took, this is Larry now, taking 3ds Max to optimize the meshes and get the 10 million polygons down to 1 million without any loss of structure. And because I'm not a Revit expert, but according to him, we needed to get it down under 1 million to get it into Revit. And we also used Recap to get some point clouds into Revit so that you could see some additional structure. So with Revit, we developed a watertight mesh for reproduction of the 35 fountain heads if we needed to cast them into concrete. The last 3 items there, we've basically gone over. Let me go to the next slide, which shows the lessons learned. I think many of the same lessons here were mentioned by John Russo. We did a site visit and we did some testing before committing to this project, although we didn't know if the items would come out in as great a detail as they happen to be after this testing. So also the fact that the sensor details are important, that you look at them to be sure that in the event that you have a problem, you have multiple sensors there to produce a product that the client, in this case, the GSA, was very interested in because they didn't think we could do it. Visualization for this was very important, and the clouds, the sun, and the time of day were important because the Artec Leo couldn't really operate in super bright sun. So we were there early and in the late afternoon. We also did not have any tripod footprint problems because we didn't use any sensors that generated the tripod footprint, which would have interfered with the visualization that we obtained. And the last item, which may be important, but we used significant processing power to reduce the post-processing time that we had would have had, if we had used some different computing processing hardware. Okay, the last item is a view from nearby my house at the park up Huailo Ridge, East Honolulu, 6:30 in the morning. You can see Maui and Molokai and Lanai in the background. So I thank you for listening to me. Hopefully, Gene, I'm in my 10-minute mark.
Fantastic, Dennis. I only hope to be doing what you're doing at 82. It's and overall, just what an incredible series of presentations. This is the dream team right here. If you want to see people who are pushing the limits of 3D laser scanning all around the country, at least, and probably the world. So there's some things in the Q&A. Let's see, with the NavVis VLX, I don't know about this. What happens with people approaching you to inquire as to what it is or what you are doing? What do you think, Marek?
I mean, I can tell you, I wish I got $1 for every person that asks a question. Because there's, if a device looks like Star Wars, and then people ask questions all the time. So it's better when you have 2 people on site. If you scan, public spaces like Walmarts, for example, and our clients scan hundreds of Walmarts every year, people are asking all sorts of questions. So it's better to have a person giving an answer while somebody else goes ahead and scans, because it's a great icebreaker to meet people, but when you're scanning, you don't have the time.
Right, you don't really want to meet people at that point.
Yep.
Okay. So in the chat, let's see, you answered something in there, right, Michael?
I did. It looks like Linda had asked a question about 3D printing and materials, I think.
Okay.
So
Can you recap that?
Yeah, I mean, we do quite a bit of 3D printing and digital fabrication in general to make reproductions of things. And there's every material you could need, including the stone, like we showed. You can't 3D print stone, but you can 3D print patterns to then ultimately make things like stone-like materials. But you can also use the same data, whether it's going to 3D printing or to any other conventional digital fabrication tool, such as a milling machine, a CNC machine, or things like that to make actual objects, or to make patterns or molds, for example, to mass produce items. 3D printing is if anybody's not familiar, it's really come a long way. It's 30 plus years old at this point. There are hundreds of materials that you can use to make 3D printing. There are many different suppliers of the equipment. We don't do 3D printing in our facility. We actually outsource anything we need like that because it's just so readily available, more or less as a commodity. Once you have a digital file, you can simply upload it to many dozens of sites and get quotes and select your materials, and it'll show up in a couple of days from FedEx.
Wow. Okay. So I have one general question. We won't take too long for each person. Just give me a couple of quick minutes on each, but just one around the horn, so to speak. What's the status on what's holding things back, the hardware or the software? Where are we? What's in front of what? What needs to come up to meet the other? And you're on the screen, Michael, so I'll go with you. Hardware or software?
I think it's software. We spend, hours in the field, but we spend days doing post-processing, depending on what the output needs to be, especially if it's a 3D CAD model. There's no automated approach. I think you're familiar with some tools, Gene, that are out there that people are working on, but that's what takes, I think, the most time.
Right. John?
I agree completely. It's the software side. There's a huge need for more automation to reduce the man hours to process this data. That's things like what NavVis has now is amazing, how much time that saves, not just in scanning, but also in the post-processing, registering that data. Just loading it and then having it pop out registered saves so many man hours. Now you got a point cloud, you got to do something with it. We need automation for that next.
Right. Okay. Dennis?
I agree with John. I think that the information that we capture as quickly as we did on our Cascade project, we were able to process that internally on the equipment I showed you very quickly, and our total time, like I said, was 20 minutes. The scanning that we did with the ZNF was a little longer, but the automation in software, like John says, is going to be most important.
Excellent. And Marek?
Yep. So software definitely, the more automation, the more use cases you can get out of it, and the more affordable each marginal unit. But also, hardware, getting smaller lasers. Like our lasers cost a couple $1,000s a piece. There's no need for this laser to be so big. In 5 years from now, they will be smaller, more accurate, lighter. You can mount them on smaller devices. Eventually, we'll put all LiDAR in construction hard. You'll be wearing a hard hat with multiple lasers, and you'll be able to scan a construction site just by walking. So I think the push needs to come from both sides.
Right. Yeah. Certainly from the autonomous vehicles LiDAR side, they're working on some small designs for lasers and LiDAR. So that's definitely coming. Go ahead, Dennis.
Yeah, one thing I forgot to mention about the software, NVIDIA has released a trial on GitHub, which reduces the time to do photogrammetric type of visualizations to seconds instead of hours.
Wow.
And so that's something that people should be tracking moving forward.
Yeah, amazing. No, so just want to thank everybody. John Murphy, give you a final word, and we'll call it a great day.
Absolutely. Thank you to all our panelists. That was an incredible exploration of these difficult projects.